you would get, the name of the process. Okay, so here you have the conditional variance. Okay, so just summarizing it up. Okay, so the conditional variance of the process. Okay, since basically sigma squared was defined in the previous section, so the conditional variance of the process depends on the squares of previous realization of the process. Okay, so that's why basically the process gets its name from. Okay, autoregressive. Okay, so because here you have basically the lagged versions here of the square of the processes, so that's why it's called autoregressive. Conditional because you have the conditional variance, okay, being time dependent, okay, and heteroscedasticity means that basically the variance changes, okay, so the variance changes over time. If it was homoscedastic, then it wouldn't. Okay, so that's basically where the process gets its name from. Okay, so autoregressive. Okay, so here this is the autoregressive part. Okay, and this is basically the conditional variance. Okay. Right? So autoregressive, conditional, heteroscedasticity, meaning that the variance of that is going to be changing. Okay? All right? You understand where the name is coming from? Okay? And again, this is used basically for capturing these clusters. Okay? And I would like to show you this property. So this is relatively easy to show. I mean, the first thing is basically that you have to recognize that the conditional expectation of the process is 0. Okay? So the conditional expectation of the process, given its past, okay? So given the past of the process, as we have seen before, is 0. Now, if that is the case, then basically the variance of the process, or the conditional variance to be precise, okay? So the conditional variance of the process, given its past, okay? So given the past of the process will be equal to the expectation of the squares. Okay, because the variance is basically the expectation of the squares minus the square of the expectation. Now, if the expectation is 0, then basically you would have that the variance is equal to the expectation of the square of the process. Okay, and conditionally on. Its past basically meaning that the past of the process is already there. Okay, so the variance equals expectation of the squares minus the square of the expectation. Okay? And the expectation is 0, so that's basically how you would get this. Okay? Now, yt squared is basically you would have, I mean, this is, let me just put it in here. Okay, so the square here is going to be equal to sigma squared times epsilon t squared. Okay, that's the square of the process yt. Okay, again, the process yt is defined as sigma times the noise, right? So if you take the square of it, then this is going to be the square of the product is the product of the square. So this is going to be what you would have for the process given the past. Okay. Now, guys, here you have the following: that this expression here, since it's an autoregressive expression, meaning that it depends on the past of the process yt, okay, it's basically already known. So if you have the observations here, the previous observations here of that one, because this is what you have basically here in the equation of the process, so let me just summarize it here. So sigma, okay, so we have basically that sigma squared was equal to alpha 0 plus alpha 1 times yt minus 1 squared plus etc. plus alpha q times yt minus q squared. Okay. So right? So here basically you have that in this case you have basically already the past of the process. Okay? So if the path of the process is known, then basically the value for sigma squared is also known at point t already. Okay? So then you could just get it out of the expectation operator. So this will be equal to sigma squared times the expectation, okay, of the square of the noise. And the expectation of the square of the noise is basically, okay, so this is basically equal to 1, okay? So that is obviously equal to 1, right? So that's basically what all you have, okay? So the conditional expectation of the process is equal to sigma squared, okay? Right? So that's what you would get. And that varies over time, okay? Because the path of the process is already known. Okay? So the path or the square of the squares of the path realization of the process will give you, okay, the current conditional variance of the process. Okay, so that's how basically the variance or the conditional variance is time dependent. Okay? I mean, depends on the corresponding observation, so it changes by time, let's say. Okay? Now, and that is of course equal to, this is what you would have here, that is equal to realization. So here you have alpha 0 plus alpha 1 times yt minus 1 squared, okay, plus etc. etc. And then we have alpha cube times yt minus q squared, okay? All right. Now, obviously, okay? So that's going to be the first property, okay? Now the second property is that, we will look at when is this process stationary, okay? Again, so the unconditional variance is always time dependent, but not necessarily the conditional variance, okay? And we will look at, the following stationarity condition, okay? So question, under which circumstances is a autoregressive conditional heteroscedastic process stationary? Again, the conditional variance is time dependent, but the unconditional variance is not necessarily time dependent, and there are conditions for that too. Okay, so I will summarize this by the next proposition. Okay, so the next proposition tells you that, okay, so let's say y, the process, okay, is an arch process, and this is stationary. If and only if the following condition holds, okay? So basically you would have that 1 minus alpha 0 minus alpha 1 minus alpha 2 minus blah 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 minus alpha q is greater than 0. Okay, so this means that basically 1 minus alpha 0 minus alpha 1 minus alpha 2 blah blah blah. So you take all the coefficients and then you sum them up and you subtract them from 1, and what you would get is basically greater than 0, which is equivalent to that the total sum of all coefficients, okay? So the total sum of all coefficients is going to be equal or going to be less than 1, obviously. Okay, so if the total sum of all coefficients is less than 1, then 1 minus the total sum of the coefficients will be, of course, greater than 0. Okay, so both conditions are equivalent. All right. Okay, so that's basically the first condition that you would get. So that is only true if the total sum of the coefficients is less than 1. Okay, that's the first stationary condition. And if it's stationary, okay, so if, and I will add here this to it, so if the arch process is stationary, okay, is stationary, then you would get, okay, then basically you would get that the variance, I mean, of course the expectation is 0, the autocovariances are 0, okay, but the variance will be not 0. Okay, so the variance, and of course, it will not be time dependent either. Yes, you got a question?
Why you're starting J at 1? What if
Yeah, I forgot because I messed it up. That's why. Okay. Okay. So that's the reason. Okay. Okay. So I mean, no, I forgot. I messed it up here. Okay. So that's the coefficient that is no longer there. So 1 minus alpha 1, alpha 2. Okay. So the intercept is not there because the intercept is basically always, I mean, this is always greater than 0. Okay, and the variance will not depend on that. Okay, so if the process is stationary, okay, so then you would just all sum up the autocovariances. Then you would basically get that the variance of the process is going to be equal to alpha 0 divided by 1 minus the total sum. Okay, so 1 minus the total sum, okay, starting at 1, not at 0. Okay, and the total sum of the coefficients. Okay, I don't have much space. I try to do it again. Mess it up. Okay. So here in this case, this sum, the total sum here, basically has to be less than 1. If the total sum is not less than 1, then the variance will be negative. Okay, so then basically that the intercept is taken out here. Okay. Now let me just illustrate that why this is. Okay, so this is what we need to look at. Okay, so why is that basically? Okay, so how would you capture the variance of the process? Okay, now, okay, so let me show you why this is. Okay, so basically you would have that the variance of the process, okay, is equal to the expectation of the squared sigma. Okay, so sigma squared, right? And sigma squared is basically, you would have that this is going to be equal to, and here this is what you have, the expectation of alpha 0 plus alpha 1 times the square of yt minus 1, and then plus, and the last one will be, okay, I always run out of space. Okay, so alpha q times yt minus q squared. Okay, so you just plug it in here. Okay, so this is just a process. Okay, now the expectation of the sum is of course equal to the sum of the expectations. All right, so basically you would get this is equal to alpha 0 plus alpha 1 times the expectation. Okay, or yt minus 1 squared, right? Okay, so then plus alpha 2 times yt minus 2 squared, etc., and then you have alpha q times the expectation. Okay, I run out of space again. Okay, so the expectation of the square here of that, so this is going to be yt minus q squared. Okay. Now, of course, here you have, I mean, basically that. Okay. I mean, this is quite obvious. I mean, the expectation of the process is 0, so this is going to be also equal to the expectation of yt squared, right? So, and if you wish to make the variance time independent, okay? So if the process is stationary, that's what we have. So if the process is stationary, then these expressions here do not depend on time. All right, so then you would get that, okay, so I'm talking about these expectations here. Okay, so that one and that one, okay? All right, so that this means that basically you have alpha 0 plus alpha 1 times the variance, okay, of yt minus 1, and then you'll have alpha 2 times the variance of yt minus 2, etc., etc., and then you have alpha q times the variance of the process at point t minus q. Okay. So alpha q times the variance of the process. And again, at point t minus q. I mean, here we have basically the variance, okay? And here and there, all right? So, and the variance should not be time dependent, okay? All right? So if the variance is not time dependent, okay, then basically you would get, this is that you can replace that with, okay? So the variance of yt minus 1 would be just as large as the variance of yt. You understand? So the variance of yt minus 1, yt minus 2, etc., yt minus q will be just as large as the variance of yt. Okay? So here in this case, if the process is stationary, okay? So here you have that alpha 0 plus alpha 1, okay, so times the variance of yt, and then plus, etc., plus alpha q times the variance of yt as well, okay? So again, the process will be basically stationary. So if the process is stationary, that the variance of the process does not depend on time. Let me just write it down here so that this is equal, okay? So that this is equal to the variance of the process, obviously. Okay. Now, if that is equal to the variance of the process, all we need to do now is we need to solve it for the variance, okay? So we need to solve it for the variance, okay? So again, I mean, this is relatively easy, okay? So we put all these expressions here to the right. So then you would get basically that alpha 0 is going to be equal to the variance of yt, and then minus alpha 1 times the variance of yt minus alpha q times the variance of yt. Okay. All right, so time minus, etc., minus alpha q times the variance of yt, which is going to be equal to alpha 0. All right, so if you factorize for yt, then you would basically get to yt times 1 minus alpha 1 minus alpha 2, etc., okay? And then minus alpha q is equal to alpha 0, okay? So then you would basically get, this implies you would basically have for the variance is that this is alpha 0 divided by 1 minus the total sum here of these expressions. Okay? So that's what you would get here. Okay? So here you have alpha j's, and j starts at 1 and stops at q. Okay, so that's going to be the variance of the process. Okay? Okay, so since, I mean, we have to make sure that the variance is not negative, okay, we would basically get that 1 minus the total sum, okay, of all coefficients except for alpha 0 is going to be greater than 0, okay, so this expression, all right, this is greater than 0 by definition, okay, and if that is greater than 0, right, then of course basically that the variance is not negative, so then the process is stationary. Okay? So we take out alpha 0. That was a mistake. Okay? Obviously. Okay? So that's one of the basic properties of the process. So as you can see, although the conditional variance is time dependent, right? The process can be still stationary. Okay? Very important. Okay? So this is an effect that you would get here. Okay? All right. Now, basically, what you would do is, I mean, how you would recognize it. You know, how you would recognize a process, and this is what I also to emphasize here. Okay. So I mean, okay. So look at the process here. So yt is equal to sigma t times absolute t, where sigma squared t is equal to, then you have alpha 0 plus alpha 1 times yt minus 1 squared plus etc. and etc. And then you have alpha q times yt minus q squared. Okay, you've seen this quite a lot of times. Okay, so if I take the square of these, okay, of that expression, okay, so you can replace that with, then, okay, so we define a noise, okay, so we define, let's say, a noise, and I'm calling this Et, okay, so Et will be equal to the difference of the squares, okay, of the two. So I'm taking the square of that one minus the square of that one, okay? And if we can, I mean, if you consider this, okay, so then basically in the first equation, then basically it is possible to rewrite, okay, so the autoregressive conditional heteroscedastic process as an autoregressive process of the squares, okay? So basically you would have that this is equal to, and then you'll see this here, so this is alpha 0 plus alpha 1 times yt minus 1 squared, and then the last one will be alpha q times, okay, sorry, alpha q times yt minus q squared, and then plus et, okay, and et is, you know, that little noise there, okay. Okay, so you can see this, okay? So basically this means that in particular, okay, so if a process follows this autoregressive conditional heteroscedastic process, then basically it means that this implies an autocorrelation of the squares, okay? So basically if, let's say, okay, so here you have that the process follows this autoregressive conditional heteroscedasticity, then this means basically that the squares will be autoregressive, okay? So, I mean, if the squares of the process, okay, can be represented by an autoregressive model, okay, then this might indicate that there are some arch effects, let's say, involved here for the original process. You understand this? Okay, so that's basically how we need to recognize it. Okay, and that's basically what volatility clustering is about. Okay, so the squares basically depend on previous realizations of the process. Okay, so and that's how volatility clustering can be achieved. Okay, so that's how you would basically examine that whether or not the squares of the process can be represented by means of an autoregressive model. Okay, and if the squares of the process can be represented by an autoregressive model, it might indicate, okay, I'm not saying that this is proof of that, but it might indicate that the data, okay, is conditionally heteroscedastic. Okay, so basically that the volatility of the process, or the conditional volatility of the process, depends on previous realization of the process. Okay, so that's how you would basically examine that. Okay, I'm going to continue next week. Okay, so that's where we start. Okay, and please do not forget your assignments. Okay, all right. So you have to implement an estimator. Okay, that estimates the first order autoregressive process. It's relatively easy to do so. Okay, so you all you need to have is like little sums and division whatsoever. So it's not going to be complicated. All right, but yeah, please make sure that this is going to be the case. It can happen, guys, that next week the lecture will cancel. It can happen. I'm not sure. If the lecture will be canceled, then it will be rescheduled. Okay, so don't worry. We have more time than we basically need, but it can happen. Okay, so just for you to know, I apologize for that. Okay, I will keep you informed. Okay, so by the beginning of the next week, whether or not the lectures next week will take place. So if the lecture does not take, or the lectures do not take place, then we just continue 2 weeks after that. Okay? All right. So just for you to know. Okay. Okay, guys. Now that was it for today. Okay.